Alright everyone, welcome to today's episode of Physics QBits, where we'll be talking about how to deal with constraint forces in physics problems. So we know that we spend a lot of time calculating forces in physics. Some of them have formulas, so for example, we know that the gravitational force on some object depends on its mass m times the gravitational acceleration it's experiencing, right? We know that the force applied by a spring is proportional to the spring constant k times the amount that the spring has been stretched, delta x, right? So the more I stretch a spring, the stronger the spring force gets. But mysteriously, we have some forces that don't have formulas. So for example, the normal force, we don't have a formula for. The tension force, we don't have a formula for. And the last one that I'll talk about is the static frictional force. And so what that means is because these forces don't have ironclad formulas that work in every situation, we have to be careful when we do problems where we'll need to solve for them kind of in between, or if we want to know the tension or the normal force at the end, for example, right? So let's spend some time today just understanding how to treat these forces a little bit better in problems. All right, so these three forces we mentioned are part of a class of forces called constraint forces. They have this special name because what they're responsible for doing is maintaining some kind of condition on some object. And so a really nice example of this is thinking about the tension force as a constraint force. So let's imagine a situation in which we have some object hanging from the ceiling. We'll just say it's a brick of mass little m. And let's see if we can figure out what the tension force is using our usual four-step method for solving force problems. Okay, and so remember our four-step process starts with a free body diagram, or an FBD. The next thing we're going to do is write down the associated Newton's second law. So we're going to look at what the net forces are in the x and y directions. Next, we're going to think about constraints that we're going to have on our system. And finally, we're just going to solve, because by this point, if we've done everything correctly, this is just an algebra problem at the end. And so starting from our free body diagram, we can see that this object has a gravitational force pulling down, as do all things on Earth, right? So we have some m times g pointing downwards. We also know that there's a tension force pointing upwards of some unknown value. And this is our free body diagram, right? We have our one non-contact force, which is gravity, and we have our one contact force, which is the rope pulling up. There's nothing else touching our object, and so that means that our free body diagram is now complete. And so the next step is going to be writing down the associated Newton's second law. So remember, Newton's second law tells us in both the x and y directions independently, the net force should tell me about the total acceleration of the object in that direction. And so I can write down these guys like so, right? And what I want to do is actually look at my vectors and figure out what the net force on the left-hand sides of each of these ought to be. And so because our object is only really in the up and down direction, right, nothing interesting is happening in the x direction, we know that trivially there's no forces in the x direction, so we have 0 on the left-hand side, and there's no acceleration in the x direction. So we have this trivial equation, 0 equals 0, nothing interesting is happening here, right? But if we look at the y direction, we know that we have a tension force pointing up, so I'm going to write plus t. We know we have our gravitational force pointing down, which gives us our minus mg. And this should tell us what the total acceleration is in the y direction. And because we don't know what the acceleration is in the y direction yet, we'll leave this as m times ay, right? And so next, we need to think about our constraints. So this is the really tough part of a lot of these problems. In this case, it's not so terrible, but I want you to pause here for a moment and think about the following question. What constraint is our brick subject to? Go ahead and pause here if you want to think for a second. Okay, great. So hopefully you came up with the answer that we know that based on the setup of this problem, because the brick is just hanging there, the rope is preventing the brick from falling, right? In other words, mathematically speaking, we can express this constraint as something like the acceleration in the y direction of the brick is 0, just from the setup. This thing is just hanging from the ceiling. And so the reason this is useful is now we can simplify our Newton's second law equation a little bit, right? We can take our one useful equation, t minus mg equals may, and now that we know the constraint is that this thing is not moving, we can replace the right-hand side of this with just a 0. Then we can add mg to both sides and do our usual algebraic thing, right? And we find that the tension force must be equal to mg. Maybe this shouldn't be too surprising because we know the rope is the one thing that's trying to keep this brick in the air. And so what that means is the tension of the rope has to be exactly enough to oppose gravity and nothing more. Otherwise, this object would be accelerating, right? And so what I want you to do now is think about what happens if we have the same scenario and we use the same rope, but instead we switch out the brick of mass little m for a brick of mass big M. What I want you to do is pause here for a moment and try to predict what the new tension in the rope should be with this new system. Okay, if your guess was that the tension is equal to capital Mg, you're exactly right. This problem looks really similar to the one we did before, but just with a big M instead of a little m, right? So we have the same free body diagram. We have our tension pointing upwards, and we have our gravitational force pointing down. We know that the Newton-second law equation is going to look very similar. We have, once again, plus T minus capital Mg is equal to MAY. We have the identical constraint, right? This object is still not accelerating, and so we can vanish the right-hand side of this equation. And once we have that, we can then solve our equation as before by adding mg to both sides. And we find that the tension is equal to capital Mg, which is hopefully what you predicted before. And if not, that's totally fine too. The point I want to make is that even though we have the same rope, we put a different object on it, and now the tension in the rope knew that it had to be different. And the reason is because we need to focus on the constraints here. Because the constraint is still identical, that the acceleration of this object has to be 0, the tension has to provide exactly enough force to maintain that constraint, right? It's not like the rope knows how much it's supposed to apply, it just knows that the brick can't move. What I want to draw your attention to is that this means when you're solving problems and thinking about constraint forces in problems, you always want to start with the constraint itself. If you can accurately express the constraint, you can always just solve for any of the constraint forces you need. Okay, earlier I said that the normal force is also a constraint force. This argument turns out to work the exact same in the case of the normal force. A really nice simple exercise to do is think about two bricks on a table, one of mass little m and a bigger one of mass big M. You can follow this exact argument again and try to find what the normal force is in either of these cases. What you should find is that the normal force is smaller in the case of the small brick and larger in the case of the large brick because once again, the table has to quote unquote change the normal force to maintain the same constraint on these two different objects. What this means is as you go through practice problems, pay really close attention to what the constraints are in each problem. At rest and constant velocity are two really common ones. These both tell you that the net acceleration in some direction has to be 0. Then, once you've identified your constraints, you can simplify your Newton-second law equations and solve for any constraint forces. It turns out, in any complicated problems, you can actually get yourself in some hot water if you try to just guess what all the constraint forces are without starting from the constraints themselves. Okay, that's all I have for constraint forces like tension and normal force. Earlier, I also mentioned that the static friction force is a kind of constraint force, but the static friction force is its own beast entirely, and so we'll have a video just focusing on that force itself. If you have any questions left over, please feel free to leave them in the comment section below, and I'll try to get to them. If you want some more practice, please check out the Office Hours series where we'll work through some more complicated example problems and practice using some of these ideas. Don't forget to like and subscribe for more free physics problem-solving tips and tricks. This has been Physics Tutoring Quantized.